For the case of the closed loop positioning control system, usually we use the servo motor. As we mentioned before, when we talk about the motion control, we say servo motor is used with the servo drive in order to control the closed loop or a positioning system here. So usually for here, this servo motor can be either electrical servo motor like in AC or DC, or also hydraulic servo motor. The speed through the motor is available and controlled by the amount of the current, or in the case of the AC or DC servo motor, and in the case of the hydraulic, the amount of the fluid. Usually the motor are connected to the spindle and the table here in order to rotate the spindle or the table of the CNC machine. So the position sensor, here, which measure, we said the main difference between open loop and closed loop is the existing of sensor, and this sensor usually used to measure the current or the actual position in addition to the, and give it as a feedback to the controller. So the position sensor here, it will be continuously monitor the movement and send the feedback signal to the comparator in order to compare between the actual or the actual position and the set point that given to the controller. So as we can see here, um, unlike the stepper motor that only has a unlike the stepper motor that does not have any feedback, here we have a feedback line, and this feedback line use optical encoder as a sensor. So you can see here, this is the optical encoder which measure the or monitor the position of the table here, for example, or the position of the spindle, then give it as a feedback signal to the comparator, and this comparator will be a part of the controller for the servo motor, or the servo the servo controller here. So this compare the input value, which is the desired value, and the output or actual value here, and based on this comparator, it will give the output again to the servo motor in order to adjust the position if it's not exactly the same as the desired or the required position. So the servo motor and feedback curve measurement are used to confirm the final position of the work table. So that means it will be more accurate than the position the open loop system. So usually the closed loop is more accurate, and also it's compensate for the error that may occur in the open loop system. So in this case the error is less, so and the system output is more accurate, and the actual position is almost the same as the desired position of the system. So the encoder that we use here as a sensor to sense or to monitor the position of the table or of the spindle here, we call it its type is optical encoder, and it's a device used for measuring the rotational position and also the speed. So the common feedback sensor here for the closed loop NC control system, and it's used as a feedback. So usually how this sensor is operate, or how this encoder is operate, there is a light source and there is a photocell here which receive the light source, and when the light go through these holes or these slots, it will touch the photocell and it will generate a pulse. This pulse will send to the controller to be converted into the current position or the velocity of the rotating shaft here. So this we call it the encoder disk, and here we call them slots, and here we have the rotating disk. So it will generate a train of pulses, and this train of pulses will be converted into a real position coordinates or into a real velocity of the rotating shaft or rotating motors. So for the closed loop positioning system here, there are also some formulas that used to perform calculation according to the optical encoder here. So in the optical encoder, the angle between the slots in the disk is alpha, also it's equal to 360 over ns, where alpha is the angle between the two slots. As we have, for example, here we have one slot for example, and this is another slot. Between them there is an angle, also with the other angle there is an angle, with that slot we have an angle, and so on. So in order to calculate this angle of the between the slots, it's 360, because the total angle here, or the whole disk, or the whole in this encoder disk, is 360. So in order to find the angle for each slot, we need to define or divide 360 over the ns, which is the number of slots in the disk. So if you have 10 slots, so the alpha will be 36, for example. MB here, which is number of pulse sensed by the encoder emitter on the receiving side. I mean, since we have source and we have light source here, and we have encoder here, photocell, which detect the light. If the light pass through the slot, so this photocell will receive the light. Okay, so it can count, that is one pulse generated. So the number of pulses generated here with time, which is mb, is equal to a over alpha. Alpha is the angle here, which is in degree per slot, the angle of the slot, which is degree per slot, and a represents the angle of rotation for the encoder shaft that is rotated, this one. So the angle of rotation for this encoder shaft. X here, which is the work table position. In order to calculate the displacement of the work table, I mean the how or what is the distance that the work table will be moved towards or away, so is equal to P times MB over NS. So B here represents the lead screw pitch, which is, as mentioned before, in the case millimeter per revolution when we talk about the lead screw. Okay, and MB here is represent the number of and I mean the pulses, and NS is slot, number of slot here, when this MB is number of pulse sensed by the encoder. So NS is number of slots, MB is the number of pulse, and B is the batch. So then if you want to find the linear velocity or the work table velocity here, which is VT, as we mentioned before in the open loop. So VT here is equal to FR, or the feed rate, which is in millimeter per minute, equal to 360 time, equal to 60 times P times FP over NX. So this is how to calculate the speed of or the velocity of the work table movement here. So this is how fast this work table move away or far to the servo motor or from the servo motor. The pulse train here generated by the encoder is compared or are compared with the position and feed rate specified by the part program. So in the part program we are going to define the feed rate, and this is the feed rate here. It will be defined, and also the position will be defined as a coordinate. Then the encoder here will compare these two things, which is the position and the feed rate, and the difference between them will represent the error that will be sent to the servo driver, the servo drive. As we said before, it's like a controller for the servo motor, and this controller of the servo motor is connected with the main control unit, or the machine control unit. As if you remember, we go back a little, so just to highlight, when we talk about this part of the controller, of the servo drive. So here in this part, actually, when we talk about the servo drive here, we say this is servo drive, which represents the direct controller of the servo motor, and the signal here, we are talking about the encoder now, because we are talking about the servo motor, then the closed loop. So we are talking about the encoder, and this encoder which is attached to the pole screw or the lead screw here, and which move the table. So usually this all signal, there is also a the signal will be feedback from the servo driving here, or the servo drive, into the controller or the machine control unit. So the closed loop is good for milling and turning because of the reactionary force that resists the movement of the table. So actually, since there is a force which is resist the movement of the table, so we need to get a feedback about the actual or the current position, and also to allow the driver, I mean the servo drive, to adjust the position to the correct position that is required by the milling and turning machines. There are three parameter or three criteria or three metrics that used to for the precision of the NC positioning system to define how accurate the system, how what is the accuracy or what is the resolution or repeatability of the system. So that these three measurements are the control resolution, and actually the control resolution is the distance spreading two adjacent addressable point in the axis movement. So you have usually this control resolution also we use it with the when we talk about the analog to digital converter or digital to analog. I mean the analog to digital converter or digital to analog converter. So we talk about we or we focus on the resolution here because it's give you the how accurate the signal will be converted from analog into digital or from this value into bits or binary values. Okay, so control the resolution here. If you have 2 points on the axis here, so there is a spreading distance between these 2 points, and this as the resolution is small, that means it will give you more accurate movement for the machine. As we said before, if the machine move from the zero of origin to this point, I want to move it to this point directly, it will give you not that accurate path. But if it's move just very small steps, I mean with a too close point to each other, so our resolution, I mean the segment here becomes small, so the resolution here will be high, and I mean the error will be less. The second is accuracy, the maximum possible error here that can occur between the desired target point and the actual position taken by the system. So if I give the coordinates for the system, I mean for example to reach to this point, but the system or the machine generate the coordinates is at this point, so the difference between the actual the desired value and the actual value, it represents the accuracy, how accurate is your system to the given feedback to the given input. I mean the difference between the desired value and the actual value, it will be measurable or measured at the accuracy of your system. Repeatability here, which is defined as point plus minus 3 sigma of the mechanical error distribution associated with the axis. So this is like a constant, I mean like a constant value here, which is depends on the value of the sigma, which is plus minus 3 sigma. So as we can see here, so here is like to represent what is the accuracy, what is the repeatability. This is repeatability, this is the accuracy, and here is the control resolution or CR. So control resolution here, the difference between the 2 points. So I mean as we make these 2 points are close or two coordinates are close, we are going to decrease the control resolution, so it's make the system more accurate at this value here. And you can see here the accuracy is the difference between the desired position and the actual position or the addressable point or position. So this is more on the accuracy of your system here. This is the desired position that we want, and this is the addressable point for the first signal or the first pulse. This is the addressable point for the second pulse or the for the second signal here on the linear axis. So as these 2 points, I mean the desirable point, are too close to each other, we are going to decrease the resolution. The CR resolution will be decreased. The accuracy here will become accurate because they you do like which equal to, because accuracy is equal to CR over 2 plus 3 sigma. So the CR here, when we see have the CR is small, that means the value here will become smaller and the error will become smaller. so the machine can move from one coordinate to the another coordinate with a little or with smaller error. Repeatability here, that means how these coordinates will be repeated, or this motion will be repeated at each point. So for example, this signal is identical with that signal. That means we are going to repeat the same movement for the machine at these 2 points. I mean, it's like the same. The coordinates will go up, then go down, go up, and go down. So usually the repeatability here is a measurable. It's like it will gonna be to be added to the when we calculate the accuracy, which is plus 3 sigma. So repeatability here equal to plus minus 3 sigma. These indicators actually represent like a measurement which used to define the accuracy, or how accurate or how reliable is the positioning system of NC machines. I think these are some of the formula that used to define I mean the either the control resolution or accuracy or repeatability here. So the control resolution for the first or for the electromechanical part. When we talk electromechanical part, that means the part which is related to the rotational part, which is the motor here, or the shaft, or the lead screw, and which involve also with plug to the motor shaft. But we have another control resolution, which is more related to the machine itself, and here I mean to the computer itself, which is the computer control system, CR2. Here we have CR1, here we have CR2. So for the computer control is more related to the conversion from digital to analog and analog to digital, because the output of the controller here, usually we say the controller is connected to the actuators, and then we have sensors, correct? Here we have process, for example. Okay, let's complete the circuit. Okay, so here the output, usually this, if this is one in the controller, the input to the controller must be digital values. Even this sensor will give analog values, but it must be converted into a digital values to be fed to the controller. Then the controller will send the signal as a digital output, because usually the controller is only work with digital 0 1, 0 4, 0 volt, for example, 145 volt or 12 volt, depends. And so this value, I mean binary or digital values, when sent to the actuator here, the actuator cannot be, if the actuator is a motor, for example, so the motor is required analog signals. So after the controller here we have analog, I mean digital to analog converter, which is DA, digital to analog converter. Digital to analog converter, that means it will convert the digital values into analog value, the digital output from the controller into analog to be control the drive or the machine here, the rotating bar. So how accurate this digital to analog converter, for example, if my analog values, for example, is 7 volt, but the actual value was 6.8 volt, was x.5, I mean 6.08 volt. So usually, if we can see here, I mean if we want to convert 7, I mean 7 volt here, and I want to convert it from decimal or from analog voltage into train of binary number 0 1 1 1 0, for example, and so on. So this is accuracy here, or resolution is related to the analog to digital converter and digital to analog converter. Okay, we may have two, like we call it the signal conditioning circuit. One at the input of the controller, which convert the analog signal into digital signal, and one at the output of the controller, which convert that analog, I mean the digital signal into analog signal. So the motor here, the servo motor, will take the analog signal from the controller. But how accurate is this value to the desired value? It depends on the resolution of this computer or controller of the control system. So here we have two type of resolution, one related to the electromechanical part and one is related to the controller part of the servo motor. Since we have the servo motor and we have also control servo drive or servo control. So actually there is no we do not have example about this one for converting this is the define the full L is the full level define of the voltage. It will give you the full range of the voltage that required. For example, 2 to the power of PB is the number of bits. So for example, if I want to convert the output signal into 4 bits, I want to convert this 7 volt into 4 bits. So I'm going to find the level and I have the input level is 10 volt, for example. So 10 over 2 to the power of 4 minus 1. So this will give me the resolution or the control resolution for this analog to digital converter, for example. Here in the case of the mechanical, this all value already or parameter already used. For example, for the pitch, for the screw, lead screw, and the number of pulses, and also the gear ratio. For that we call it electromechanical because it's involved with the gear and the coupling between the drive the motor camshaft with the lead screw that will move the table and increase the velocity and movement of the table. Okay, so L here in this case will for this value here will be axis range and it will be measured in millimeter. In the case of analog to digital converter, this R represents the voltage and it will convert. It will be measured in volt. But in the case of the NC positioning system here, we're talking about the movement. So L represents the full range of axis or the full axis range, and B here number of bits of the devoted bits storage registry in the controller of the drive. Both equation can be used for open or closed loop system here. So the control resolution will equal to maximum of CR1 and CR2. Typical here value of for the control resolution is 0.00025 millimeter. So this will give you, it's like as I told you, the resolution here is more on the difference between the 2 points. So this is my first coordinate, this is my second coordinate. What is the distance between them, or what's that? As we can see here, this is the first or the addressable point, the first addressable point here, and the second addressable point here. The distance between them is related to the CR or the control resolution. Accuracy is equal to CR over 2 plus 3 sigma, which is the standard deviation here. I think that's all about this chapter. So next we are going to start with chapter 3. Okay, we are going to stop here.